logistic regression, the most popular model for binary classification. It was first introduced as a mathematical transformation of the linear model to solve classification tasks, but then introduced many inconsistencies and challenges that eventually gave birth to a whole new statistical field. And in this video, you'll learn how it actually works and why it is the gold standard for many fields. Part 1. The sigmoid. We'll start with the name. Logistic stands for a family of machine learning models that take the form of an S shape, which are bounded between two values. Examples are the hyperbolic tangent, the sigmoid, the sine function, and many others. Regression stands for predicting a continuous variable y. It seems counterintuitive at first because our target y in classification is a binary outcome, but regression in this case refers to the process of predicting probabilities. It will make more sense by the end of this video. Because there are many functions to choose from, logistic regression is often associated with the sigmoid function, which takes this form. If you stare at it long enough, you'll notice something strange, mainly this part at the bottom. It looks exactly like the hypothesis from our linear regression video. The sigmoid is just a transformation of the linear line, with the intent to squish the output predictions to the range 0 to 1. And just like linear regression, the unknowns here are the parameters theta. If we look at a simple example like the academic performance, on the x-axis the hours spent studying, and on the y-axis the outcome of that student, passed or failed, our sigmoid function will look like this. The x here is our input data, and the only variables are the parameters a and b, and just like before, vary the a to stretch or squeeze the sigmoid, vary the b to move it around. If we add another feature to our example, like the sleep hours, and how they affect the final outcome alongside the hours studied, the data will look like this in 3 dimensions. Now there is one trick teachers often use to visualize this in 2 dimensions, and that is to look at it from above. The labels here get mixed up, so it's hard to tell which is which. We solve this by using colors for our labels y. Also, the position and the rotation of the sigmoid function can be visualized by this line. This is called the decision boundary, which is just the line passing through the center of the sigmoid shape, often denoted as z equals 0. This is the positive region, and this is the negative region. Part 2. The update rule. Our objective boils down to finding the best parameters for the sigmoid function just so it sits exactly on top of our data. That's what training a model means. Your computer needs 3 main components to achieve that: the data set, the model space, and the update rule, so it can pick the best hypothesis from the provided model space, and it does so by optimizing the parameters. You might have heard of Newton's method or the Bayesian approach, but in this video we'll go with the maximum likelihood estimation. Since you're studying engineering, you probably want to know how it works in action. The likelihood is a way of telling how likely any distribution resembles the current observed set of data, given that you started with some initial guess. So you start somewhere, calculate the likelihood, then guess again. This looks arbitrary, so we definitely need a solid framework that allows us to somehow iterate that initial guess to land on the best parameters. And luckily, the likelihood function offers just that. Because it is concave, we are guaranteed an optimal value, and we know how to navigate concavity from our multivariable calculus class. We'll use gradient ascent here. Before we do that, we have to first arrive at a form we can work with. The likelihood function is the product of probabilities for all points of their y's given their inputs x, and the initial sigmoid guess, theta. Put simply, at any point from your training data, take a wild guess of how the sigmoid should look like. Then predict its label y. Do that for all points and multiply the results. Before you say that predicting the labels that we already know is a stupid idea, let me tell you that our end goal here is to arrive at an UpdateRule formula. So we'll have to trick the math. Unfortunately, we have a problem here. This notation is vague. We don't know what label we're calculating the probability for. Is it 0 or 1? So we'll have to simplify this. Because of the way the sigmoid is shaped, the probability of y equal 1 is just the output of the sigmoid function, and to find the probability of y equals 0, you invert the probabilities by taking 1 minus the output of the sigmoid. Now we have a second problem. We actually need both of these in one formula, so we can run operations on them. Luckily, we can use a mathematical trick to achieve that. Now that our likelihood is in a good form, unfortunately, we have a third problem here, and that is float overflow. Some of these probabilities will be small. Taking their product will get harder for your computer as your data grows, so we'll need to handle that. We'll use the log likelihood to convert this product into a summation, and since it's monotonic, the objective remains the same. Using some algebra, we can simplify this. This function is concave, and the only variables here are the parameters of the sigmoid function. To iterate this, you take its derivative, then use the gradient ascent to find this update rule. Now you initialize all your parameters to some number. Then update and iterate till you arrive at the local maxima. Congratulations, you have found the best parameters. Put them back in the hypothesis equation. You now have a trained model that is ready for production. We can now use this model to perform inference, like finding out the probability of a patient having a heart attack based on his cholesterol levels. Because it is called logistic regression, it will output probabilities between 0 and 1, and it is our job to convert them to whole numbers. In classification, we usually care about the category. So unlike linear regression, there is no generative task here. We'll end this video with a homework. First question, why is the likelihood function considered concave? Second question, how does the float overflow happen exactly? Third question, explain why the likelihood increases when the guess sigmoid is close to true data, and why does it decrease otherwise? Last question, if the data is completely separable, what stops the machine from continuously increasing the parameter a to infinity? Note that the parameter a is responsible for squeezing or stretching the sigmoid. Hint, the solution is done using regularization by putting constraints on the parameters. Write your answers in the comments section. We'll end this video here. If you learned anything, consider subscribing. And if you want to support the channel, you can find our Patreon in the description below. Thank you for watching.